Thank you very much for the invitation. It's great to talk in this audience. Yeah, today I will talk about Polyhedral Omega, which is an algorithm I will explain later for solving linear Diophantine systems, and I will show how we can use this to do optimization. So you can interrupt me anytime you want. I will most probably not finish in time anyway, so I will stop when time is over. So to motivate, and also because one line of research of the methods we will use comes from the theory of integer partitions, let's first see what integer partitions are. So we have a non-negative integer n, and we want to write it as a sum of positive integers. For example, the partitions of 4 are these 5 partitions, possibilities, either 4 or 3 plus 1 or 2 plus 2, 2 plus 1 plus 1, 1 plus 1 plus 1. And we sort them. So 1, 3 is not different than 3, 1. We sort them in descending order, which means that x1 is greater than x2, greater than x3, etc. And they are all non-negative integers. So we can add zeros afterwards, it doesn't matter, right? Now, let's see partitions of 5, but we restrict the number of parts. So we say we only want 2 parts. So then we have 3 such partitions, 5 plus 0, 4 plus 1, and 3 plus 2. For example, 3 plus 1 plus 1 is not a partition of 5 in 2 parts because we have 3 parts. And I will already start showing a bit of geometry. These 3 points are these points here, right? Now, according to what we saw earlier, what we want is x1 to be greater than x2 since they are sorted, which means that we are in this area here, in this shaded area. And since they are partitions of 5, we want their sum to be equal to 5, which means we want the integer points in the intersection of the blue area with the red hyperspace, which is a line in dimension 2, hyperplane. So essentially what we want is the lattice points, the integer lattice points. When I say lattice points, I mean points with integer coordinates in this intersection. Okay. The question is, which partitions satisfy such conditions? We want to enumerate them all. Enumerate here, I mean list them. Tell me which ones they are. Now, another problem is a problem of computing the integral flows. What is an integral flow? So let's say we have a network, which is a graph where each node vi has some excess bi, we call it. We assign an integer to its node, and each arc, its edge, has a capacity ci. Now, a feasible flow is an assignment of values to the arcs, such that for every node, the outgoing minus the incoming arcs is equal to bi, which is the excess of the node, and the value we assign to its arc is less or equal than its capacity ci. So let's say we have this network here. The conditions are that we have to find x1, x2, x3 such that xi is smaller than ci, and the excess. So here, for example, in V3, we have 2 incoming nodes, arcs. So minus x1 minus x4 and 1 outgoing x3. So x3 minus x1 minus x4 must be whatever the excess value of V3 is, V3. This is a problem that will fit in the net framework we will discuss. And also we want this to be, so the integral part is that these have to be non-negative integers. And we will see that this makes the problem quite different. More combinatorial problem, let's say we have 3 by 3 symmetric magic squares. What a magic square is the row sum and column sums are equal for every row and every column. So if we write it as a system, and we decide that R is the row sum and column sum, and by the way, since it's symmetric, that's it's already said, rows and columns don't matter. So what we require is that every row is the sum is equal to R. And we can write this as a system here of constraints. Okay, we can ask two questions which are different and both important. One is how many, and the other is what are they? What are they is exactly the same question as the one I asked for integer partitions. How many is a slightly different question. Now, the way we count stuff, one way we count stuff is generating functions. So let's say we have a set S, and we want to represent it in a nice way. So Herbert Wilf in generating functionology says that generating function is a clothesline on which we hang up a sequence of numbers for display. So now, let's say we have this infinite set, all the non-negative integers. Then we have an infinite clothesline, which the way we implement that is by introducing a formal variable z. We put the sequence in the exponents and we sum up. So essentially, we have a formal power series, which is the phi of R set, the formal variable z, is this formal power series. And okay, now if in general, I will care mostly about sets that contain vectors. So let's say that S is a subset of Z to the D. The definition is the same as before. We take all the elements in I and put them as exponents in Z, but now Z is Z1, Z2, ZD. So this is a multi-index notation. And if there exists some rational function such that it has an expansion equal to that formal power series, then we say that this is a rational generating function for the set S. And we will care a lot about rational generating functions. Now, the example that we had before was that of natural numbers. The formal power series is this, and it's easy. I mean, this is the geometric series expansion formula. We know that this rational function has this as a series expansion. So this is the rational generating function for the natural numbers, 1 over 1 minus z. And essentially, that's the only one we will need to do the geometric things we want to do. Now, going back to the 3x3 magic square, symmetric magic squares, the generating function for the enumerating problem is this. Now, if we expand this as a series, in the exponents of the z variables, we will get 6 exponents, which correspond to the 6 values that make this into a magic square. If we want to count how many there are, then we have this counting function. Now, how do we go from enumeration? Let's say we know a set. It's easy to count the elements. So when we can enumerate, we can count how many solutions we have if we know the solutions. That's a bit not true, but in general, let's say it's acceptable as a statement. If we want to use generating function, in the enumerating generating function, the exponent of each monomial corresponds to a unique solution to our system. Now, if we want to count the number of monomials, we can set every zi equal to 1. And then every monomial will contribute 1 to our sum, and the sum is the number of monomials we have. The only problem is that in this rational function here, sorry, 1 is almost always a pole. So we will have to do something smarter, which I will not talk about in this talk, but it's possible to do the correct substitution there in order to get the count correctly. Another way to go is to do a refined counting. So we want monomials. So we will count the number of monomials that have the same total degree. How do we do this? By putting every zi equal to q. And this is what I did here. So here, if we expand this, we will get a series in q. And the coefficient of q to the t tells us how many monomials of the total degree t we have. We can also use a different substitution for a different grading. This is something people in algebra like to do a lot. Now, let's go from counting to optimization. So an optimization problem is a set of constraints C and an objective function F. Intentionally, I'm not giving too much information about what these are. What we want to do is find an X such that the constraints are satisfied and f of x is maximized. F is maximized by x. Now, let's assume that we have such a problem and we have a lower and an upper bound for the optimal value. Optimal value is the value of f of x when this is maximal. Now, if we have such bounds and a black box, which we can ask how many solutions give a specific value are greater, how many solutions do we have that give values greater than v? I don't care for the moment how this happens. We have a black box, an oracle asking. Then what we can do is a binary search. So we check how many solutions do we have if v is the midpoint of the two bounds. Now, if we have 0 solutions, then it means that this is beyond, so v is above the optimal value. And we set the upper bound to our old v. Otherwise, we increase the lower bound. And this way, we will find at some point the optimal value. We repeat this process until either the two bounds are equal or some other termination criterion is reached. And actually, this sounds like we don't always have bounds, but it doesn't really matter because we can always find an upper bound by doubling. So we pick a number. If we have solutions, then we double it until we find an upper bound where we have no solutions anymore. Okay. Now, I said I didn't explain what kind of constraints do we have, because I want to motivate a bit the fact that we are talking about linear problems for the rest of the talk. Hilbert's 10th problem asks if given a Diophantine equation in any number of variables and with integer coefficients, can we devise a process according to which it can be determined in a finite number of operations whether the equation is solvable in rational integers? So essentially, in modern language, this asks, is there an algorithm to decide if a Diophantine equation has solutions, is solvable? And Matijasevich in the 70s, based on previous work, mostly by Julia Robinson, proved that the problem is undecidable. So there is no algorithm to decide if a polynomial has integer solutions. So let's say a bit the landscape of Diophantine systems. By the way, yeah, Diophantine means that we want non-negative integer solutions. As we saw from Hilbert's 10th problem, here in the dark side, we have a polynomial asking for integer solutions. We cannot decide that. Now, in the orange part, we have decidable problems. So there exist algorithms. And here we have a variety of different complexities. For example, if we want to decide if this equation has non-negative integer solutions, this actually is solvable in polynomial time. This is a very nice, so this is a specific problem. So if I give you a number n and ask you, is this, are there x and y non-negative integers such that this equation holds? What am I asking about n? I see you smiling.
Quadratic equation, of course.
Sorry?
Quadratic equation.
Yeah, but I mean, what we want here, we ask about n if it is prime, right? So if it is, so this is primality test. So, and this was proven to be in polynomial in P. Now, if we fix the dimension and we have linear systems, and we ask for non-negative integers, we're still in P. But if we want linear without fixing the number of variables, then we are not, well, if P is not equal to NP, then it's not solvable in polynomial time anymore. A linear problem with integer solutions, then this is solvable in polynomial time by different matrix decompositions. Okay, so it is not totally unreasonable to restrict to linear problems because the complexity is already bad enough. So the formal definition is that a linear system of equation inequalities where the coefficients are integer and the solutions are non-negative integers is called a linear Diophantine system. And the kind of solution we want to find is an expression for the rational function, a rational generating function representing the set of non-negative integer vectors that satisfy our system. Okay, so now we have a problem and we know what type of solution, what the solution is for us. Let's see the tools. So I will go through the definition from polyhedral geometry really fast. A polyhedron is the intersection of finitely many half spaces, and if it is bounded, then it's called the polytope. A cone is the intersection of finitely many linear half spaces, which means that they go through the same point. And if the generators of the cone are linearly independent, then the cone is called simplicial. Now, if we take the determinant, so okay, we have this fundamental parallelepiped, which is this region here. If these are the generators of the cone, the number of lattice points in this region, half-open region, it's called the index of the cone, and it's equal actually to the determinant of the absolute value of the determinant of the generator matrix. If this is plus minus 1, then the cone is called unimodular. And just for terminology, we have the different faces of a polyhedron. So if a zero-dimensional face is called a vertex, a one-dimensional edge, and a d minus one-dimensional face of a d-dimensional polytope is called a facet. And a vertex cone, which is the most important definition for us today, is the smallest cone where the apex is at the vertex of our polyhedron. And this is the smallest cone that contains our polyhedron. So for example, this is a vertex cone, or this one is a vertex cone for this cube. Okay, now we want generating functions and we want to connect them to lattice points in polytopes. So let's see, the first step is to find the generating function of for the lattice points in a simplicial cone. I will start enumerating the points. So here I have the generators are 1, 0, and 1, 3. Right? And I will start, so 0, 0, this is Z1 to the 0, Z2 to the 0. Then I have the point 1, 0, which is Z1 to the 1, Z2 to the 0. And then Z1, 2, 0, 3, 0, etc. Right? And then I can also use the second generator and I get the point 1, 3. And I will use then the first generator again to have 2, 3, 3, 3, 4, 3, etc. And I can also use the second generator again to go to 2, 6, and so on, right? So in general, I can use k times the first generator and L times the second. And now I enumerated all these blue points, right? And it's not hard to see that this formal power series, right? So if this is the generating function, this is the rational generating function. We just split in two, and this is geometric series. If we expand this as a geometric series, we will see that we get that. So great, but we still didn't count all the points, right? Because, for example, the points here, 1, 1, is not included in this list. Now, what we will do is take this semigroup, the blue part is a semigroup, and we will shift it by 1, 1. Shifting by 1, 1 just means that we take whatever we had and we add 1, 1. And I can factor out this, Z1, Z2. And now I can gather these two things together, which are the same. And this means that just this Z1, Z2, the point where I moved, appeared in my numerator. And I will have to do it again for the 0.12, and now I covered all the lattice points in this cone. So this is the rational generating function for all these points in here. And the observation is that the numerator is actually the generating function of these 3 points. So 0, 0, 1, 1, and 1, 2. And this holds in general for any simplicial cone. The rational generating function is given by the numerator being the generating function for the lattice points in the fundamental parallelepiped, and the denominator being this product of 1 minus z to the generator, product over all the generators. Okay, so this means that if we have a simplicial cone, we know how to write down the generating function. Good. Let me show you a trick. If I have array starting from, this is the natural number, right? So 0 to infinity, we discussed that this is 1 minus z. Now, if I start pulling, I pull a minus z in the denominator, and I move it in the numerator, etc. So what happens is I can see these green points as the expansion of this one. So I'm expanding in the direction z to the -1, and I start from the point -1. So I don't start from 0. But also I have a different sign. So what this means in geometry, in polyhedral geometry, we call this working modular lines. So if a polyhedron contains a line, then its rational generating function is 0. Because if we sum them up, we get 0. So let's see how this can be used. Let's say we have this pentagon, and we want to find the rational generating function for the lattice points in there. We will do the following. We'll start with a plane, and we will remove these half-open cones. When it's dust, it's open. So I think we agree that what remains is our red pentagon. So let's see. Now, we will use this trick of flipping array. We said that we change the direction, we change the openness, and we change the sign. So let me say again that this was closed and it becomes open. If we go in the other direction, it was open and it becomes closed. So here, if I change the direction, if I flip the direction of this array, I will change the sign and I will change the openness. Here it was open, now it is closed. And if I do this for all 5 cones, what I get is this, and these were exactly the 5 vertex cone of the pentagon. So now, what we said is to get the rational generating function for the lattice points in this pentagon, we just have to sum up the rational generating function for the vertex cones of the polygon, right? Here's another example. For this polytope, we just need to take the 4 vertex cones. So one is here, the other is there, here, and there, and write down the rational generating functions. Let's take, so for example, this one is a rational generating function of the cone corresponding to the orthant, right here. So I know because these are 1, 0, 0, 1, the generators. Or this one is which one? It's the one from 3, 4. And the generators are -1, -1, and -1, -2. So, and if we sum up these 4 rational generating functions, actually we get this polynomial, which the exponents in this polynomial are exactly the blue points in here. Okay, so that's just an example of how Brion's theorem works. Good. And now it makes more sense why here I'm saying an expression for the rational function, because we will allow to have a sum of rational functions, right? Good. Now, I will go through partition analysis really fast, because we will use a very crucial idea from there. So partition analysis was introduced by MacMahon in beginning of 20th century. And for example, it's exposed in combinatory analysis from 1915. And there, actually in his partition theory memoirs, says that if we have a function f in two sets of variables, z and lambda, and we expand it in ascending powers of z, then we forget all the terms that contain negative powers of lambda, and we put lambda equal to 1. What we get is a function only in z. And we will represent this by omega of f z lambda. Okay, now this sounds not very reasonable, but we will see how he used it. By the way, this comes from invariant theory, where Kelly used it. So the way MacMahon used it is, given a linear Diophantine system, he constructs this Crude generating function, which is a multisum where we have our original variables x, y, and we introduce one new variable for every inequality. And as exponent of this variable, we put the inequality itself. So here we had x minus y minus 1 equals 0. We put this as exponent here. And for lambda 2, we have 2x minus y minus 3, right? Okay, now let's remember what omega was. It says expand and reject all monomials that contain a negative exponent in lambda, in some lambda. So this means reject all the monomials for which x and y does not satisfy the system, right? So we'll keep only monomials where x and y satisfy our linear system. So now we can take this multisum expression and write it as a rational function. It's actually, again, just using the geometric series expansion formula, right? From there, we can just move from here there. And partition analysis was dealing with how we apply this operator on such a Crude generating function. And there are different versions of this. So MacMahon gave one based on previous work of Elliott. Then for many years, the method was largely forgotten until Stanley used it again in the 70s. And in the late 90s, Andrews and Paule revived partition analysis. And with RISA, they gave also, combining with symbolic computation, they gave an implementation for the method. So if we go back to the symmetric magic squares example, this was our system, which means that this is our multisum expression. So I put the constraints as exponents in the new lambda variables. And I want to keep track of what is happening for the variables. And I also want to know for which magic number R this is a solution. So if I apply omega on this, what I get is the generating functions I showed you earlier, right? This is how I computed them. So, okay. There are no questions until here?
No, thank you. Not from me.
Great. Then I will show you now what omega means geometrically. And by the way, let me say that, so this is work from my PhD, but it's also joint work with Felix Breuer. So I will only use one inequality in two variables because I can only draw in 3 dimensions and I need 1 dimension for every variable and 1 for every equation inequality. So here we say that the first step is to, so if we take our system A and B, right? I will prepend in every column of A the corresponding unit vector, and I will prepend adequately many zeros in B. So what this means is I take the unit vectors and I lift them by columns of A. So 1 goes to, I live by 2, since I only have one element in my matrix A. Sorry, every column has one element. And then 1, 0 or 0, 1 goes to 0, 1, 3. And I will shift this cone by -5, minus the right-hand side, and I have this cone. Now, we said that we want things that have only non-negative lambda exponent. This means that in this three-dimensional representation, we have to be above the xy plane, because lambda has to be non-negative. So I find the intersection, and I keep only the things that are above. And now in here, I have some lattice points, and these lattice points satisfy the inequality, but they're still lifted. We still have some lambda. And remember, in the definition of omega, we said that we put lambda equal to 1, which means that we project to the xy plane. We forget about lambda. And now these points are exactly the solutions to this inequality. So polyhedral omega is a method that computes a representation for the rational generating function of this polyhedron. The first step is exactly as trivial as we discussed before. We just prepend a unit matrix to our matrix A and the 0 vector to B. And then the second step is actually more interesting. Now, what we did is take the intersection with things that are non-negative in lambda, right? So if we take such an intersection, and now this is not a three-dimensional, you have to think higher dimensional picture here. I intersect with this hyperplane, and I want to keep only things that are above, right? So I want to keep this green polyhedron. But the way I want, the description I want of this polyhedron is actually Brion decomposition. So what it means is I need the two vertex cones of this polyhedron, the blue and the red cone. Now, because at the next step, I will take these cones and I will cut again with the next lambda coordinate until I have no lambdas anymore. So now let's take the red one, right? How did this came to be? We had our apex, right? We had this cone. So V1 we know, because this was the generator of the cone we had before. V3 we also know. W1 is not hard to compute, because this is where this vector intersects our hyperplane, the hyperplane we cut with. W2, the same. This is the intersection of the hyperplane with the V2 vector. And now essentially G1 is what we need to know, right? And G1 is actually the vector, the intersection of the hyperplane defined by V1, V3 with our lambda equals 0 hyperplane, with the hyperplane we cut. So the point is that the Brion decomposition, so Brion decomposition now, what we need to describe it is the apex and the generators of every cone. So this is the only interesting vector, and it's given by an explicit formula, because we had the VIs, and we know that the last coordinate of every of the vector must be 0. So this is exactly how to obtain such a vector, G1, G1. So in general, GI. So all the vectors are just computed using linear algebra. I mean, not even linear algebra, just combinations of this type. So, okay. The next step was to find the lattice points in the fundamental parallelepiped. And for this, we have two ways to do it. One is to enumerate the fundamental parallelepiped explicitly using such a formula where these V's and W's are coming from the Smith normal form of the generator matrix. And I don't want to go into details about that, but it's conceptually still easy. We just transform our fundamental parallelepiped into a different space where now it is a rectangular parallelepiped. And there it's very easy to enumerate the points, right? And then we map them back to our original space. So original basis. So the other alternative is to use Barvinok's algorithm, which would be at least one talk in its own. The main reason I'm mentioning it because this was the first. This is an essential component for the fact that if we fix the dimension, which means the number of variables, then the algorithm I'm showing here is a polynomial time using Barvinok's decomposition. So, of course, in order to, so all these tools to enumerate stuff in the fundamental parallel pipette are needed in order to write down the rational generating function. But so we had the apex and generators, and we want to get the rational generating function. But what else we can do is just keep the cones, right? Do not write them as rational generating functions. So the output is shorter because these rational generating functions may have large numerators. You may see a pattern. These are the positive sides, but it's not a rational function, which usually is a good thing for combinatorial problems, for example. So, yeah, as a summary of the algorithm, so we took elements from polyhedral geometry and from the partition analysis side. And what we did is, so in the geometric side, to enumerate all the vertices in edge direction and to triangulate the vertex cones, this is computationally hard. But we don't need to do all this just by using the MacMahon lifting, these new variables. Introducing new variables solves the problem. On the other hand, in partition analysis, it was hard to evaluate the operator, the omega operator, by using analytic rules. Instead of doing that, we just use Brion decompositions, so the geometric tools that simplify these operations a lot. Now, I want to return a bit to the concept of symbolic cones, which is just the matrix of generators, the apex of the cone, and the 0, 1 vector just telling us which facets of the cone are open. So, like the ith element of this vector is 1 if the facet not containing the ith vector is open. So this is a very compact representation. This is very easy to compute. In all examples we have, when we run Polyhedral Omega, computing the decomposition is very fast. Computing the rational function is what takes ages, since it's a hard problem. We can do symbolic manipulation at the geometry level. It provides structural information. And the good thing is that it's not a rational function because it's short. And the bad thing is it's not a rational function because it's bad because cancellations do not happen. So in the rational function level, a lot of cancellations may happen. So simplifications. So, okay. And let me go back to the original part where we will use this for optimization. So let's say we have these two inequalities as our constraints, and we want to maximize this functional. So this is, okay, here was, I didn't see another typo until here. So now here is my typo. This is x plus y, right? Yes, it's x plus y. I want to maximize x plus y. So because this vector is the 1, 1 vector. So the way I do it is I take this red half space, right, which is defined by minus x minus y smaller or equal than alpha, some value alpha, which I don't know, right? And I start moving it up and down. So the moment here, for example, I have no solutions anymore. So I know that the optimal value must be smaller than that. So here, for example, it's okay. Here is okay, but here it's not. And now I will do this binary search I explained in the very beginning. So here we have a system of 3 inequalities. The main difference with the example I showed before is that we have a variable here. Instead of having some, instead of the right-hand side being a coefficient, a number, it is a variable. So what are the generators of the matrix of the cone when we do the MacMahon lifting. So we prepend the unit vectors to these columns. So 1, 2, minus 1. Is it really so wrong what I wrote here? Okay, so I changed the order. So the order is, we read it in the different direction. So minus A, this would be minus 5, right? And now, so I think here I mixed the sequence. So because this should have been, so if I didn't change the sequence, it would be 0, 1, 1, 2, minus 1, 1, 0, 2, 1, minus 1, and 0, 0, 5, 5, 0, 0, minus 5, minus alpha. Okay. So, but when, so this is our original cone. And I did the first elimination. So I had 5 coefficients, remember? I was in 5 dimensions. And now I eliminate the last dimension. And what I get is a Brion decomposition, which is this cone plus this cone minus that cone. And if I eliminate once more from 4 coordinates, I end up with 3 coordinates. I have a Brion decomposition, which is this cone plus this cone minus this cone minus that cone. Now you see, I cannot eliminate once more because I don't know, since here I have an alpha A, I don't know, remember in my cone, I assume that I'm cutting here. But if I don't know where the apex is, I don't know if my hyperplane is below or above. So I actually have to specify alpha before I can eliminate one last time in order to have a cone in 2 dimensions. So what I will do is specify alpha equal to 2. If I do this, I get these cones here. So these cones here tell me I have a Brion decomposition is this cone plus that one minus the red ones. Okay, and these are the lattice points that lie in this polyhedron. So the way I computed it is by actually computing, I used Polyhedral Omega for that, our implementation. So we computed the generating function, and these are the points. This is the generating function, so these are the points it corresponds to. So I have many points. I can actually try now for 4. But if I put A equal to 4, what I get is empty. So there is no point because 4 would end up somewhere here. So we have no points. So 4 is too much, 2 is too little. Let's try for 3. This was the binary search idea. I have these 2 cones minus that cone, which is the 2 green minus the red. And I have these 2 lattice points. Okay. And so actually, I think I changed this wrongly because the rest of the solution is correct. And these are the optimal values. These are the optimal solutions, and 3 is the optimal value for this problem. Okay, so combining. So in the binary search, I said that we need a black box. Now our black box is this decomposition of our solution space, where we can ask how many solutions do we have if A is greater than 3, right? So the advantage of doing this, by the way, is that here we eliminate as many constraints as we want until we reach the constraint that corresponds to the objective function. We don't have to re-solve the problem every time we specify a value. We only solve it once. We only eliminate one more time for every value we try. Otherwise, all the other constraints we solved symbolically once, and then we can try as many values as we want. So are there questions until here? And I think I'm fine with time, right?
So is there a bound on A so that the list is not empty? Is it so?
Sorry?
Do we have, is there a bound or is there a bound on A in
This is
terms
what
of the
we're testing.
coefficient?
So, for example, here, if we would try for 0, for example, definitely there are solutions. So that are greater or equal than this line here, right? But if I move, where was 4? 4, it would have been here. So I would take, okay, let me try to annotate. So if it would be here, in this region here, right? Then the intersection is empty. We have nothing in there. And since 4 is too big, we will try 3, which is smaller. And there we will have solutions. So now how do I know that this is, I can stop there? That's a good question. So if I know that the optimal value is integer, I tried for 4, I tried for 3, it cannot be anything else, right? So it's smaller than 4, so it has to be 3. If also 3 was empty, then I would go for 2.
Stepwise algorithm.
Sorry?
This is stepwise. You decrease stepwise. So
yes. So I'm really doing just binary search. So I have an upper and a lower bound, and I go in the middle and I ask, do I have solutions in the upper part? If I don't have, I will focus on the lower part. If I have, I will split now this and do the same recursively. So yeah. Now, how we implement, so one big question is, can we detect from the Brion decomposition if it is empty or not without computing the rational function? That's a that's a question I care to have the answer. So are there more questions if I answer the previous one? Okay, so now where do we go from here? First of all, we want efficient implementations of both the Polyhedral Omega algorithm, which now we have a Sage implementation. It works, but it's not amazing. And also the one to do the optimization. So then another advantage of this method is that when we're given a problem, we have a geometric decomposition into cones of its solution space. So we can analyze the geometry of the solution space of the feasibility problem of the program. A direction I didn't mention at all today, but I'm very interested in is to generalize the Polyhedral Omega method to work in a dimension that is not fixed. So until now, we said that the input is this matrix. Now, what if I can describe a matrix without telling you the dimension? So I give you a family of matrices. I'm saying the AN is described in this way, and N can be anything. Now, I want to solve the problem for AN, where N is part of the input. And there we will need rewriting techniques. And we're currently setting up a reading group about rewriting techniques, and then we want to work on these topics. But that's a rather different direction from what I discussed today. And finally, apply to combinatorial problems, because of course, integer linear programming method cannot compete with the excellent heuristics we have today, right? Because this is a general method. So it's not expected to perform better, except for specific families of problems where the geometry, for example, helps, or this is something we have to actually investigate. When is it worth to check if using Polyhedral Omega helps? Okay, thank you. And I will also advertise shamelessly a conference for the summer. Thank you very much for listening.
Thanks for a nice talk. Any questions from audience? So by the way, this scale workshop is very interesting and it has many sessions as far as I know, and some of them are very much related about our institute topics. So maybe this year it will be face-to-face workshop. Last 2 years it became online, but this time it will be face-to-face, and fortunately it will be in Istanbul, Gebze.
Hope, yeah. I will hope it will be face to face.
Yeah, it will be.
It's that was our hope. So the idea was to gather as many people as possible after 2 years of pandemic.
This is 13 or this is the ongoing. I mean, this is the what is the number? Which now? This is the 13th or 3rd.
So actually, in scale, we have at least 2 conferences inside. So 2 big conferences. One is applications of computer algebra, and I think this is 27th, and computer algebra and scientific computing, which I think is
31.
I don't remember exactly the number, but yeah. So these are long-standing conferences.
Yeah, long-standing conference. I mean, so last year it was online, but
Vienna in theory.
in Vienna, yeah, it was in Vienna, and I remember one was in Barcelona. So this year it will be in Istanbul, and Professor Zafeirakopoulos will be local chief editor of this conference. Yes, any questions? So I have one, maybe I can ask. So in your interest in polytope and number of integers in this polytope, so can you think about the volume, or can we think about the density of this lattice, so that can you say anything about us, about your solution? What about its density?
So so counting the number of lattice points in a polytope is called also the discrete volume, because if you change the lattice, okay, so this goes towards Erhard theory. So in Erhard theory, we are asking how many lattice points we have in dilations of polytopes, right? So I take a polytope, and then if I double it, how many lattice points do I have now? So if I take a square, the unit square, I have 4 lattice points. If I double it, so 0, 0, 0, 2, 2, 2, 2, 0, now I have 9, and so on. So in general, I have t plus 1 square. So this is Erhard polynomial, and this is essentially equivalent to saying that I shrink the lattice by 2. So, and if you shrink and shrink and shrink, where you end up is the actual Euclidean volume. I think this was, so the question was the connection between volume and lattice points, right?
The number of, yes, so the number of lattice points in a polytope is nothing but about appears as an exponent in your polynomial, as far as I remember.
In what, so
in polyhedral algebra, so you obtain a geometric expansion, so you obtain lattice points as an exponent in your polynomial. Lattice points.
What is in the volume polynomial?
Not in the volume, but in the polytope. So in the polytope, you have some lattice points. So lattice points they appear as an exponent in your polynomial.
Yes, yes.
Yeah. So does it any meaning about in terms of this volume, in terms of density of the lattice points with respect to this polynomial representation? So, but
I don't think
maybe
directly. So directly from the generating function, I cannot say directly from the generating function, but what we can do is go from the generating function to the Erhard series, and from the Erhard series we get the Erhard polynomial. By the way, for algebraists, this is Erhard series is Hilbert series, and the Ehrhart polynomial is a Hilbert function. So there, the leading term, the coefficient of the leading term in of the Ehrhart polynomial is actually the volume. So there is a connection, but I cannot go directly from our generating function there, but we have to go through some evaluations.
Cryptography also interested in lattice and lattice volume of lattice. So this is somehow very, in cryptographic point of view, we work in this direction. So if there are many lattice points, so it will be, of course, discrete volume, but finding the finding the maybe nearest one would be a great problem and very difficult problem, one of the NP hard problems. Okay.
So Barvinok's algorithm actually works in shortest vector problems, etc. So it uses this kind of algorithms, LLL. So yeah.
Okay, we again thank you for a nice presentation.
Thank you very much.
Meeting us here in this presentation, and we hope to see you in Ankara face to face next time.
I also hope so.